at this thing under a microscope, this neuromuscular junction. All right, so when we're looking at it, this is a skeletal muscle. We can say the A bands and I bands, repeating pattern. This is a branch of that motor nerve coming down. And this is that neuromuscular junction, the end part of it. All right. With the light scope, it looks like it's directly in contact with the muscle cell itself. And it wasn't until we invented electron microscopes that we figured out, there's really a cleft, a space in there. But these little round things are the vesicles of acetylcholine. So we can actually see the little synaptic vesicles of acetylcholine. And then this would release acetylcholine, which would transfer the electric impulse from this to this. Now in lab tomorrow, what I'm going to use is a little electricity in a volunteer, and I can actually take electricity and make your muscles contract. Because I can use electricity to act like a nerve to cause the releases of acetylcholine. And then clinically we use that to help people with muscle problems in physical therapy with a TENS unit and stuff like that. So, all right. So what we're going to do is we're going to use acetylcholine to open these sodium channels on the sarcoplasmic reticulum. And it's going to create what we call a depolarization event that's eventually going to travel in both directions down this sarcoplasmic reticulum. Okay. So what we have is we have a really long muscle cell. And at one point along this muscle cell, we have this neuromuscular junction. And if we can initiate a depolarization event here, then eventually the depolarization can travel in both directions from where this neuromuscular junction is. So before the depolarization arrives, then we would say the membrane is at rest. And we're going to use acetylcholine to convert the membrane from rest to depolarization. Now eventually we want to reverse what we did. And so eventually we're going to do the opposite to the membrane, which is cause a repolarization. All right. So this graph is of a nerve, but the good news is we're going to talk about nerves in the next unit, and we're going to review this again in the next unit. But muscle and nerve work pretty close together. If we were going to do cardiac physiology, we would find out that cardiac muscle has a little twist to it. And we'll do that when we do cardiac in the next class. So the membrane over here is at rest. And the resting potential on the membrane is -70. So if I stimulate it, so my stimulus in the body is going to be the release of acetylcholine. Tomorrow in lab, it'll be actually using the electricity to stimulate it. So what I need to do is I need to move the membrane so that I can open a bunch of sodium channels. And so I've got sodium channels throughout the membrane as it goes away from this neuromuscular junction. And they open because of a change in voltage, so we call those voltage-gated sodium channels. So your body uses acetylcholine to initiate this process and to open a few sodium channels so that we can open those voltage-gated sodium channels. So the voltage-gated sodium channels open at -55. So what I have to use is I have to use acetylcholine to move the membrane from -70 to -55. And so since the voltage-gated sodium channel is open at -55, then we refer to that as threshold. And so I have to get enough acetylcholine released to create a threshold event if I'm going to get my muscle to contract. So tomorrow in lab, I'll use electric impulses. And if I give a person a little electrical stimulus, but it doesn't move the membrane to minus 55, then the muscle will not respond. So the goal is to move the membrane to minus 55. We use acetylcholine within our body to do that, but we can use electricity clinically to do that, okay? Like in a TENS unit. Once I reach 55, then I open those voltage-gated sodium channels, and sodium is going to rush in. So sodium is going to move via diffusion. So that was why it was critical that I had more sodium outside my cell and less sodium inside my cell. The sodium is going to move from an area of high concentration to an area of low concentration. Okay. So now, as all my sodium is rushing into my cell, what's happening to the amount of sodium outside the cell? It's steadily decreasing. So what's happening to the amount of sodium inside the cell? It's increasing. And ideally, if you understand diffusion, we would reach a point where the concentrations on both sides of the membrane would be equal and the rate of diffusion would greatly drop, right? We never reach that point. We've got so much sodium outside the cell compared to inside the cell that we rapidly move sodium inside the cell. Now, what was making my membrane positive on the outside was the sodium. What was making my membrane negative on the inside was this phosphate and cellular protein. This doesn't move, but what happens if I keep adding sodium? Then I'm going to negate those negative charges, right? So, and the fact that chloride doesn't move. So what I'm going to end up doing then is I'm going to end up reversing the charge across my membrane. So that the membrane becomes positive on the inside and the membrane becomes negative on the outside. So I'm going to go from my resting stage to this depolarization stage. So what I do is I reverse the charge across the membrane when I cause this depolarization to occur. So when we're looking at this graph, we start at minus 70, and the membrane is going to be positive on the outside, negative on the inside until we reach 0. And at 0, the membrane flips, and it becomes positive on the inside, negative on the outside. And this becomes a positive number. And so what we then do is we reach a peak of our depolarization event of plus 30. So in essence, what depolarization does is it changes the charge, the voltage on the membrane from minus 70 millivolts to plus 30 millivolts. And then the critical thing to understand is that plus 30 is what closes our sodium channels. So when I reach plus 30, the membrane essentially stops depolarizing. Close those sodium channels. But what it does is it opens a second channel, which is a potassium channel. Yes?
So at this point, you have your sodium inside the cell, your chlorine outside the cell, and your
Potassium still inside the cell.
potassium still inside the cell.
Okay. So now I have other channels mixed in with these, which are voltage-gated potassium channels. And what happens is plus 30 closes my sodium channels but opens my potassium channels. And so that's going to initiate a repolarization. Okay? So there's an event that occurs. It occurs on neurons where it's important. It occurs in the heart where it's critically important. In skeletal muscle, it really doesn't matter, but it's on the chart, so I'll just quickly talk about it. So what actually happens is we move so much potassium that we actually go beyond minus 70. So let's say we go to minus 80. So the membrane exists in a really incredibly short period of time in what we say is hyperpolarized. And then the significance to hyperpolarized is that when we're in a hyperpolarized state, the threshold changes. Okay. So normally the membrane's at minus 70. And threshold is minus 55. So what I essentially have to do is move the membrane plus 15 millivolts to create threshold. Okay. When I'm hyperpolarized, I'm setting at minus 80 millivolts. My threshold doesn't change, it's still minus 55. But now I have to move the membrane plus 25 to create an event. So essentially what hyperpolarization does is cause that requires a stronger stimulus to get a response because you've essentially changed threshold. It's not important to skeletal muscle, but it's going to be critically important to cardiac muscle.
I was curious if that's like when the muscles are tired and they're trying to stimulate a stronger response.
Yeah, it's very similar to that. What we end up with is during this bar right here, we end up with what we call an absolute refractory period. So in skeletal muscle, it doesn't matter. Cardiac muscle, that prevents another contraction from occurring. So during an absolute refractory period, the muscle wouldn't respond again. Because skeletal muscle doesn't have an absolute refractory period, it will undergo tetany, or you get a cramp where the muscle will stay contracted repeat until you can force the muscle to relax. No one's ever had a heart cramp.
Oh, yeah.
And it would kill you. That would be the end of you if your heart cramped. So the way we make the heart non-crampable is it has an absolute refractory period. That's essentially why it's critically important. Okay. So what usually happens if you work out harder than normal, you begin to go to sleep. When you go to sleep and your legs begin to relax, everybody's feet plantar flex. As soon as you plantar flex the foot, the tension on the gastroc decreases, and the gastroc says, and then you're hopping out of bed going, oh, and trying to stretch that baby out. You stretch it out, put tension back on the tendons, yeah. But you've never had a heart cramp. And if you have, you would not know. So that's the only value. So absolute refractory period is going to be important in nerves in the next unit and in cardiovascular system, but it's really not important in skeletal. So we could have ignored it. So this just reiterates what we said, is our membrane is going to exist essentially in three phases. At the top, we're starting. So we could have ignored it. So this just reiterates what we said, is our membrane is going to exist essentially in three phases. At the top, we're starting at rest. And when we're at rest, what channels are open? No channels are open, right. So when the membrane's at rest, sodium channels are closed, potassium channels are closed, but the sodium potassium pump is still doing its job, right? So it's still active. All right. So now in you, if you get acetylcholine released from a nerve and enough acetylcholine binds with enough of those acetylcholine sodium channels, that we move the membrane from minus 70 to minus 55, then we reach threshold, and then sodium channels all these sodium channels open up. And that creates an event we call a depolarizing event. As soon as the membrane reaches plus 30, then sodium channels close and potassium channels open. Or we could say activate or inactivate. And then we'll go from a depolarizing. The depolarization event is communicated deep into the sarcoplasm via the T-tubules. And what we're going to do is transfer the depolarization to the sarcoplasmic reticulum. And we're going to open up calcium channels. So now we have another